Welcome everybody. This is Smart Vision Lights, Machine Vision Lighting Basics. This is Module 4, Optical Filters and Films. I am Steve Kinney, Director of Engineering for Smart Vision Lights. Welcome and let's begin. Today we're going to talk about 4 topics in this training. We're going to talk about using color filters on a white light compared to using a colored light source. So there's some pros and cons to talk about there. We're going to talk about using notch filters to block ambient and unwanted light to get a better response out of your system. We're going to talk about contrast enhancement and using color filters or linear polarizers to sharpen details in the image. And lastly, we're going to talk about brightening films and why this matters on backlights for gauging or other metrology applications. So starting off here, we're going to talk about color filters. Color filters are typically called bandpass filters, and what you see is they tend to pass just a specific color. So we have an example of a blue 470 nanometer filter there on the top right, and you can see from the chart that all light is blocked except the narrow light in that blue area. 470 is a light blue color. So you can buy these filters in many colors through the visible spectrum, but also including ultraviolet, near infrared, and even into the SWIR spectrum. So no matter what you're doing, there are filters available to cover the areas you need, and we are showing one that I believe is about 40 nanometers wide here, but you can get them in varying widths depending on how much light you need to pass around your center color. There are 2 basic use cases for using colored filters. The first is filtering to convert white light to a specific color. And the second is for blocking, which is preventing unwanted light from interfering with the controlled lighting you're using for your machine vision inspection. First, we're going to talk about blocking ambient light. Ambient light is bad for your applications. The whole point in doing machine vision imaging is to get the right image that you need for your inspection or whatever deterministic type of thing you're doing with the machine vision under controlled lighting conditions. So we go a long ways to control the structure and type of the light and get the right image for what you're doing. But any ambient light then represents an uncontrolled source that can disrupt your controlled circumstances. So you don't want the ambient light because it's providing an offset. You can get glare from it. You can get shading. One edge of your image can become very bright. It can offset your color, upset color measurements. There's a lot of bad things that happen just from having uncontrolled lighting. So the best case, of course, is to shroud your inspection from ambient light if at all possible and just block it. But that's not possible in all cases. So then what do? There's 2 ways to deal with ambient light problems. One, just make sure your lights are brighter than the polluting light source. So if you have overhead fluorescent lights, for example, which is very common, or in factory settings they might be metal halide lights or similar like that, then you try and just in your area use very bright lighting, and certainly at Smart Vision Lights we specialize in very bright lighting, and you try and just overpower that so that your light is providing 90% or more of the light that the camera is capturing, and then you will control that. But when we talk about sunlight coming in a factory window or a roll-up door or something, this is not at all possible. Sunlight is extremely bright, can be upwards of 70,000, 100,000 lux when we're talking about sunlight on noon on a clear day, and overcoming that much sunlight at a significant level for your inspection is often impossible. So that's where we look at the second way to deal with ambient light problems, which is to use a color bandpass filter to block the ambient light, but pass the particular wavelength you're using for the illumination in your machine vision inspection. We do want to note that this works mostly for monochrome imaging. If you're doing color imaging, obviously you need a full spectrum of color light, and then using narrowband filters isn't necessarily appropriate for that, and we're left for other solutions that we're not going to talk about today. Using bandpass filters for ambient light blocking, though, is fairly simple. On the far left graph, you see a typical spectrum of sunlight, and you'll notice I've included the outside of the visible areas. So you see the visible areas from red to green to blue, and then you'll notice there's UV, near infrared, and pushing towards the SWIR end of the spectrum. Sunlight is very bright, and when we talk about 100%, then we are again talking about 70,000, 100,000 lux. And overcoming that can be difficult. In the middle graph, then, you see a bandpass filter for an 850 nanometer bandpass filter, which is just into the near infrared. And it's very common to use 850 nanometers, and that's for two reasons. Number one, you'll notice the amount of energy is decreasing as we're moving off the visible spectrum past 700 nanometers and into the near infrared spectrum in the 800 and 900 nanometer area. But more than that, if you look right around the 850 area, you see there's actually a little dip there that's pretty significant. So part of this technique involves us limiting the background light with this notch filter and then overpowering it with the light we're providing with light that's specific in that band. But at 850, besides the fact the background noise is lower just in the near infrared than in the visible, at 850 there's actually even more of a dip, so it's a little easier to overpower this area. So if we provided lighting using LEDs that are in the 850 nanometer area, which is a standard color that we do provide in many of our lights, then you can see with the notch filter on the third graph there on the right, you can see that we've chopped that little area of 850, imposed it within the area of the notch filter, and you can see that if we provided LED lighting that we would get a very strong signal there and only have a little bit of background ambient to overcome, and this is much more doable than trying to overcome it in the high percentage area of light that's contained in the visible area. It is notable, though, I've used 850 for this example, but we can do this. If it's not appropriate, you can do this at any wavelength, including red, green, or blue, and it's just there's just a little more background in those areas, and you just have to work a little harder to overpower it. But your cameras are also more sensitive, and we have bright lights in those areas, so you can use whatever is appropriate. But if you're dealing with sunlight, it is most common to use the 850 area. Some people also use the 960 nanometer, which is also a deeper color of near infrared that we have available, but it's important to note your camera is less sensitive as you move further and further out. So unless you have reason to move that far out, people typically use 850 when blocking sunlight. The same is true if you notice on the first graph, the bottom graph there on the far right bottom is a fluorescent light graph. You'll notice also if we're using fluorescent lights that they're really weak in the red. They have big peaks in the green and the green-yellow area, and even pretty strong in the blue and blue-green area, but you'll notice the red is very flat. So if you have fluorescent lights, it's even easier to apply this technique than if you have sunlight. Moving on to the next topic, let's talk about using filtering for color. Color filters versus colored light, there's two different techniques here, and there's some pros and cons to both. Color filters are very versatile. They're cheap. You can screw them on the front of your camera lens, and you can turn any white light source into a colored light as needed. And in this diagram on the right, this is actually from a color discrimination slide I use in other presentations, but you'll notice we have 4 die-cast metal cars simulating automobiles here in 4 colors, and then the top they're done in white light. But for inspection, and that was the purpose of the original slide here, for paint inspection and other things, sometimes you want to maximize the contrast to find chips, scratches, and other things. You don't necessarily want the color image, you want the maximum contrast. And that's what this slide is showing you, that in blue light, the blue cars get brighter, and in red light, the red cars get brighter and the blue cars tend to get darker. And you can use those techniques for various inspections. So if the simplest thing would be to take a white light source and put a blue or a red filter on your camera to get the effect you need for the inspection. But the downside of doing that is the white light contains a very full spectrum of light. So if I have, let's use a round number for explanation here, if I have 50 watts of white LED light and I need to do this, then I can put a red or a blue filter on there, but the red or blue filter represents only a fraction of the total amount of light energy available. So out of my 50 watts of light, I might only get 5 or 10 watts in a red or a blue area, which is much less for my camera. And often these inspections are dynamic, there's motion, and you want a fast shutter time. So color filters can be versatile and cheap, but they also block most of the available light by the definition of a color filter. Colored light, as an opposition to this, is available in many wavelengths. Down at the far bottom on the left here, you see the graph of all the colors of LED lights that we have for standard colors here at Smart Vision Lights. You can order lights in all these areas, and you'll notice they're very narrow band and very high peaks. They're available in many wavelengths. You can select, just like filters, you can select what you need, but the difference is they are the brightest and best for your fast exposure time, because by using a colored light, 100% of the energy is in the narrow band that you are after. You're not blocking any light. So if I put 50 watts of blue light down, 50 watts are going towards my inspection that required the blue light. Unlike the colored filter where we put 50 watts of white light and maybe got 5 or 10 watts in the narrowband blue area. In some cases, maybe even less, depending on the bandwidth of the filter. So colored light always is an advantage over colored filters for getting the brightest and best performance of however much money you spend on the lighting. And when we're talking about fast inspections and exposure times, you're often spending quite a bit to get the brightest light, so you want to maximize that. Nothing wrong with using colored filters, but just think about it, and buying a colored light is often the better case and bang for the buck as far as tuning your system. You also want to note that we now make RGBW tunable color lights, and that means there's a red, green, blue, and even a white reference channel in there. And you can use these to make any color, or to make a white light reference to grab your color image before you go off and make a blue or a red image for contrast. So RGBW lights actually offer you the best as far as tunability and getting the most power and band for your camera. Next, we want to talk about filtering to improve contrast, which means MTF. MTF is modular transfer function, and that's an expression of what percentage of light is transferred on your edges. So chromatic distortion is an effect that happens in cameras and lens systems, where the camera lens is bringing the light from the scene, you see in the top right diagram there, and it's focusing the light down on the sensor plane. But what happens is light bends at varying wavelengths. So the blue wavelengths actually bend tighter and harder along the optical axis, and that winds up with them projecting and making a slightly larger image on the sensor plane. And you can see that the blue on the sensor plane in that diagram is the widest. Red light is the other end of the spectrum, and red wavelengths are affected less by the same refractive index of the lens, and they tend to bend less and be focused by the lens, and that has an effect of not as much magnification when it makes it to the sensor plane. And you will notice that the red cone on the sensor plane is the most narrow and nestled inside the green and the blue. And if you think about it, most people know this intuitively. This same effect that I'm talking about is why sunsets are red in the evening. The sun is going down on the horizon, the blue light is bouncing off the Earth's atmosphere or passing straight through it, whereas the red light tends to bend around by the atmosphere and follow the Earth's curvature. So this is happening in your lenses, and this is called chromatic aberration or chromatic distortions. So when this happens, there's a slight effect. At the macro level, if you look at the image, you don't see this with your eyes, and it's not really affecting anything. But when you zoom down on the pixel level, you will start to see this effect. So this chromatic distortion causes color-dependent focal shifting on the sensor. If you're using white light, then you have all these frequencies, and the contrast will be reduced due to this chromatic lens distortion. And you'll notice the bottom image here are contrast max filters provided by our friends at Chroma Technology, and using filters like this to improve contrast, and they make specific ones for contrast enhancement here. Using a narrowband filter will help you. And what you see here is why. So on the bottom left is a typical US Air Force resolution chart that many people may be familiar with. And you see on the bottom left the full chart in the field of view with offset on the diagonal right there, and zoom in on the very bottom of that chart where you're starting to lose contrast. And you notice the numbers are becoming fuzzy. And the numbers are becoming fuzzy partly due to the optical limitations and the Nyquist limit of the optics, but they're also becoming fuzzy because of the chromatic distortions we're talking, and the fact we're using white light in this example and bending that through the lens and seeing chromatic distortion. If you look at the same images on the far right here, you can see with your eyes that with the Bandpass, this is the same chart, same light source, but filtered through the blue Chroma MV450-20 filter, and the 20 is the bandwidth, which is 20 nanometers. So this is a very narrow band blue. We're letting only the blue wavelengths through. But if you look at the zoomed in section, if you don't understand the graph in the middle and knew nothing else about this, if you looked at the zoomed in section as we go diagonal right there, you can just read the numbers with your eyes better. You can see that the 1.6 is almost sharp, whereas it's already becoming quite blurry on the unfiltered one. And if you read down by the 2.2, 2.5, 2.8, you've already lost your contrast and resolution there. Whereas in the filtered one on the right, you can still read 2.5, 2.8, and even down in the 3.2 and 3.6. So just natively to your eyes, you can see this effect is being improved as you zoomed in, and that proves that there is some chromatic effect on top of the Nyquist limits of the optics. But if you look at the graph down the middle, what we're showing you is the yellow line in the zoomed in profile is what we call a line profile. And the graph in the middle is a graph of that line profile. So as you go vertical along the left edge, that's the pixel position along that yellow line. And then what is the horizontal axis with the graph turned on its side like this is the percent or the pixel count that's being transmitted. So the bigger the deviation there, the more contrast. Contrast is the difference between the maximum and the minimum values transmitted. So if you look along the orange line, which is the unfiltered white light, you'll notice you do have contrast, and we're swinging from a high and low as we're crossing those bright background and the dark bars. But you'll notice the peaks and valleys are 100% less and contained within the blue line. In every case, as you're crossing the resolution bars, the blue line goes higher in the white value and lower in the dark value. And again, the contrast is the difference between those two values. So we're getting much more transmission and contrast through the system using the blue filters by just eliminating the chromatic aberration. The last thing we're going to talk about today is brightening films and why they're important on backlights for edge optimization. So what you can see in this example is that we have a small cylinder on an upcoming product from Smart Vision Lights, a mini backlight here. And the shaft appears smaller if you just image it in this example by the diagram on the top right there. The light, there's two effects actually that are going on here. One is the object is shiny and it's not perfectly flat. So it's not flat against the surface of the backlight, and there's light coming in from the edges which hit that curved surface and also reflect into the camera. So that makes the edge fuzzy, it also makes it appear smaller. The other effect that's in here is kind of what I alluded to with the sunset earlier, that light there's a known effect where light, as it bends around sharp edges or through pinholes, the light bends to follow the edge or form itself through the pinhole. This is the effect that we see in sunsets where the red light follows the curvature of the earth. It's also the principle that makes pinhole lenses in cameras. So both of those effects are in play there, and they have the effect of making objects smaller when we put them on the backlight or making the edges less defined and fuzzy, both of which are bad if you're in a application where you're using the backlight for metrology or for gauging and measuring things like threads, the diameter of the cylinder, or other things. So in some cases, you can make the light further away behind the shiny cylinder as the diagram is showing, but that's less optimum. You can't do that in all cases. If you have a flat part, that doesn't stop the light bending around the sharp edges and so forth. So while this can help, and we want to point this out for you as far as good imaging practices, that is not always the solution. The solution is to use edge enhancing films, which you find on our backlights. And if you see on the top left image here, the standard diffuser, if I just take the same backlight and put a very common diffuser, and this is what a lot of backlights from other makers do, then you get good diffusion, you get a good backlight, you can see the uniformity is there, but you can see the effects we're talking about in the zoomed in portion of that cylinder there. You can see that the edges are both fuzzy, you notice the threads are becoming fuzzy, you notice the edge of the cylinder is a little bit fuzzy, and then more than that, you notice that the grayscale is not black on white, but that you get the medium kind of gray along those edges, which make it hard for your machine vision to find that edge. Besides it being blurry, the lack of contrast, the fact you're going from a white background to a medium gray and not a hard black, all affects your ability to gauge in that circumstance. And there's nothing wrong with that backlight or diffuser, but what you can see is if you take the time to understand this, and manufacturers like Smart Vision Lights then do additional enhancements to our backlights, including using these brightening films for edge optimization, then you can see in the middle image where we have the edge enhancing diffuser and the zoomed in of the same cylinder, then what you see here is the threads are sharper, the edges of the cylinder are sharper, and in fact that the transition from the bright white background to the edge of the cylinder goes from a bright white to a dark edge, and there's no grayscales, and again there's less blurring there. So that of course is what we want for gauging metrology, any kind of measurements we're going to make in this system. Lastly, the graph on the far right is showing the responses of the filter and what you get with the standard Lambertian diffuser, which is an ideal diffuser there, and what happens with the edge films. And you can see from the graph the sharpness and the steepness with the diffuser and film there that's lending to the effects I described in the images themselves. So make sure that your backlights are coming from a quality manufacturer and that you're using these kind of films, or that the manufacturer is making backlights with these kind of films, because they will affect your performance. and not all backlights and light sources are equal. And this is something we strive at the design level at Smart Vision Lights to optimize for you and your applications. So lastly, I want to remind you that Smart Vision Lights, we are full service and we have technical help to help you. We have application engineers, we have people like myself doing presentations out there in the world, and we want you to know that we're here to help you win business and get it right. If you have questions, needs in your applications, be sure to contact us and get the correct technical help to get the images that are right and best for your machine vision application. That will help you get the right result out of your system or to your customer system that you're building. So we are your partner, and we want to be your go-to for the how-to in all cases when you're dealing with lighting and imaging here. Thank you for your attendance today. I again am Steve Kinney, Director of Engineering for Smart Vision Lights, and we do encourage you to contact us when you have lighting needs. Thank you, and that concludes today's presentation.